In this lecture, we will discuss about some numerical related to AC circuits. This lecture covers numerical on the RMS and average values of AC quantities. We will take some special case here. Also, we will discuss how to solve the complex numbers in this lecture, and then we will see how to convert the rectangular form of the complex number to the polar representation and vice versa. The first numerical is associated with the average and RMS value of the AC quantity. In this, basically, we are asked to find out the average and RMS value of the trapezoidal waveform as shown in the diagram here. So in this diagram, if you see that this particular quantity is associated with the voltage, Vm is the maximum value here, and it is a trapezoidal wave, which is from 0 to pi. That means the time period of this particular waveform is pi. And this waveform has three parts. This is the first part, this is the second portion, and this is the third portion of this particular wave. So we will solve this particular, numerical and find out the average and RMS value of this particular waveform by integrating this over the pi radians, means from 0 to pi, for these three portions. And we will see what is the answer for this particular question. So if you see the first part here, this one. So this first part is a triangle O, A, and E. And the first portion of this wave extends from 0 to alpha. So let us divide this whole voltage into three portions. So we have V1, V2, and V3. So here V1 is from 0 to alpha. V2 is from alpha to pi minus alpha. And V3 is from pi minus alpha to pi. Okay. So by using this, we can solve this particular numerical. So let us see what is the equation for V1, V2, and V3. Now we can use the equation of line to determine V1, V2, and V3. So V1 is, now what is V1? It is if you see here in this particular diagram, so these are the coordinates here, which are 0 and 0. This is this coordinate A is your alpha and Vm, right? So if you see the equation for V1, it is the equation could be written this way: y minus y1 is equal to y2 minus y1 divided by x2 minus x1 into x minus x1. So here, if you see, y1 is 0, x1 is also 0, y2 is Vm, and x2 is alpha, and y is V, and or V1, let us say, and x is what is x here? X is theta, right? It is theta. Okay, so then the equation would be something like this. So the equation for V1 will be equal to Vm by alpha into theta. So this is, let us mark it as equation number 1 here. Similarly, we can find out the equation for V2 also. So V2 is, now in V2, if you see, V2 is basically a flat line. If you see here, this is a flat line, right? It is from A to B, and if you see, it is Vm all the time, right? If we have to find out the height here, so it is Vm. We can use the equation for the area also. The area divided by the base length. Base length is alpha and this minus. So this would be equal to Vm. Okay, it is not changing. So slope is 0 here. So V2 is, in this case, So this is V2. This is, let us say, equation number 2. Then we can find out the equation for V3 is, let us see V3. So these coordinates are your x is pi minus alpha and y is Vm, and here it is pi and 0. So in this case, if you apply the equation of line, which is y minus y1 divided is equal to y2 minus y1 divided by x2 minus x1 into x minus x1. So in this case, y is equal to v3, x is equal to again theta, y1 is equal to, what is y1 here? You can see y1 is Vm, x1 is pi minus alpha, this is x1 here, and y2 is 0, and x2 is equal to pi. So this, if we put all these values in this particular equation, we will get v3 minus y1 and Vm is equal to 0 minus Vm divided by pi minus pi plus alpha, means x2 minus x1. And then we have theta minus pi plus alpha. So this will give me V3 minus Vm is equal to minus Vm divided by alpha and theta minus pi plus alpha. So we can simplify this equation. We will get V3 is equal to, so on simplifying this particular equation, we will take this on this particular side and we will simplify it one. So we will get V3 is equal to this one. So this is, let us, equation number 3. Now, if we see these equations, they extend from, like here V1, it extends from alpha, sorry, 0 to alpha, and this is from alpha to pi minus alpha, and this is from pi minus alpha to pi, right? So the average value of the given waveform can be obtained as, so average value formula is same. It is V average is equal to 1 upon T integration from 0 to T V dt. So this could be, here T is equal to pi. So we'll add 0 to 1 upon pi, and then this will be divided into 3 parts, right? So it is from 0 to alpha we have V1 dt, plus from alpha to pi minus alpha we have V2 dt, and from pi minus alpha to pi we have V3 dt. So we will put all the values, let us say equation number 4. So we will substitute all the values of equation 1, 2, and 3 in this particular equation. So we will get V average is equal to 1 upon pi, and then all these equations 0 to alpha is V1, which is equal to V1 is Vm by alpha into theta. So it is Vm by alpha into theta. Now this will change to d theta here, plus then alpha to pi minus alpha. V2 is Vm d theta, and then you have third forecast, which is pi minus alpha to pi, and this is equal to Vm by alpha and pi minus theta d theta, bracket close. So we can solve this equation here to get the average value. Now, if we solve it, we will get average value as 1 upon pi, and this will be Vm by alpha. This would be your theta square by 2, 0 to alpha, plus Vm, and this is your theta, alpha to pi minus alpha, plus this is your Vm by alpha, and this is your pi theta minus theta square by 2, pi minus alpha to pi. So we can simplify this equation. The answer would be, so on simplifying this particular equation, this one, we have got, now putting all the values of limit here, and on simplifying this, we have got this as the average value. This is, let us say, equation number 5. In the similar manner, we can find out the RMS value of this particular waveform. Now, the RMS value can be obtained as the formula for RMS value is under root 1 upon t integration from 0 to t v square dt. So the same concept will be applied here also. We have this as 1 upon pi, t is pi here, and then whole this equation will be divided into 3 voltages. First from L0 to alpha, V1, V1 square dt, plus second is from alpha to pi minus alpha, V2 square dt, and the third is from pi minus alpha to pi, and it is V3 square dt, and bracket close. So this is, let us, equation number 6. So we will put the values of V1, V2, and V3 in equation number 6, and we will see what is the answer. So now we'll take a square on this particular side instead of taking under root all the time. So on the last step, we will put under root on the right hand side of the equation. So we have 1 upon pi here, and then bracket start. From 0 to alpha, we have V1, which was Vm by alpha into theta, and then square of this and d theta. Then from alpha to pi minus alpha, we have Vm square d theta. And then from pi minus alpha to pi, we have Vm by alpha. Let us see what was the equation. Vm by alpha pi minus theta. So, and the square of this, and this is also now d theta, and then final bracket close. So we can simplify this equation. This is, let us, equation number 7. So we'll simplify equation 7 to find out the value of RMS of this particular waveform. Now on simplifying this, we have got, if you simplify this one, V RMS square is equal to 1 upon pi, and then this would be your Vm square by alpha square, and this would be your theta cube by 3. The integration of this would be theta cube by 3 from 0 to alpha. Similarly, you have this Vm square here, and then this is theta from alpha to pi minus alpha. Now, then we have this equation here. Now, in this equation, we can, if you see here, this one, so this would be minus Vm square divided by alpha square, and then you have pi minus theta cube divided by 3, and the limits are from alpha minus pi, not alpha minus pi, it is pi minus alpha. So it is pi minus alpha to pi, and final bracket close. So this is, let us, equation number 8. So we will simplify this equation number 8, and on simplifying this, we have got 1 upon pi, and then you have this. If you solve this equation, so we have this one with you, Vm square by 3 alpha square, and then you have alpha cube minus 0, right? And then similarly, you have Vm square, then you have pi minus alpha minus alpha. Then similarly here in this one, Vm square by This would be your, let us say 3 here, 3 alpha square, and here it would be minus alpha cube. If you simplify this equation, you'll get this one. So bracket close here. Now we can simplify this one also, this equation. If you see, these two are similar terms here. These two terms are similar. And the final answer will be something like this. Uh, or so this would be your 2 Vm square, and 1 alpha will be cancelled here by 3. So this square will be cancelled out with the cube. So there would be 1 alpha, Vm square alpha by 3 into 2, right? Plus Vm square pi minus 2 alpha. So this is again equal to, we'll take Vm square common here because it is a common term. And then we have, simplifying this one, we have got pi minus 4 alpha by 3. So VRMS is, so VRMS of this equation is, now we'll take the square root on the other side. It is Vm square pi minus 4 alpha by 3, or VRMS is equal to Vm under root pi minus 4 alpha by 3. So this is the final answer, and this you can mark as equation number 9. So this is how you can find out the solution for such type of cases. This was the special case I have taken just to make you understand how to calculate the average and RMS values of such waveforms. Okay, now if you want to find out the form factor and peak factor also of this particular waveform, that can also be obtained, because as you already have calculated the average value here, this is the average value, equation number 5, and then equation number 9 is the RMS value. Peak value you already know, the peak value is Vm. If you see the waveform, peak value is Vm here, right? So you can find out the form factor and peak factor also very easily. Now let us see how to solve the complex numbers. In our previous lecture, we have seen that a phasor can be represented as a complex number. Now, because in our AC quantities, we will be dealing with the phasors, means the phasor diagrams of various AC quantities. And phasor is a complex number, so we need to understand how to solve the complex number also. So let us see, because we know that a phasor is a line with an arrow. So if you have these two coordinates, this is the real axis and this is the imaginary axis, and a phasor is there with an arrow. So this phasor will have two coordinates here. First coordinate is on the x-axis, means the real axis, and the second coordinate is on the imaginary axis. So if this is a phasor A, which is equal to x plus jy, and you all know why we put j here, because j is the replacement of iota in electrical system. J is equal to 1 root minus 1. So this part is y, and this part is x, and this is your theta. Now this A is equal to x plus jy, it is the rectangular form. And it can also be, it is also known as Cartesian form. Right. Now to solve this equation, we only need two things. Okay. We need the magnitude of the complex number. And second, we need its phase. The first thing we need the magnitude. Second thing we need its phase. Now phase is this theta. Okay, so magnitude is modulus of A. This is how we can find out, and phase is nothing but theta, or sometimes it is also denoted with phi in some books. So don't get confused with the theta or phi. So it is phase basically, or phase angle. It is also known as phase angle. Now if you have a complex number, then the magnitude can be determined as so let us see the magnitude of this one. This is modulus of A under root, which is equal to under root square of real part plus square of the imaginary part, right? So here it is x square plus y square. So this is the modulus. This is, let us say, equal to r. Okay, let us say it is equal to r. Assume it. Now the phase angle theta can be obtained as, now we have this, if we assume this to be a right angle triangle, this is, let us say, O, and this is A, and this is, let us say, B, for example, this one. So this is a right angle triangle. So we can apply the trigonometry here. So by applying trigonometry, we will get the answer. So tan theta is equal to your AB divided by OB. So AB is your Y and OB is your X. So theta is equal to tan inverse Y by X. So these two quantities we need basically. Now, if we have to convert, so this is how we can find out. It is very simple. Whenever you find such a complex number, you can simply find out its magnitude and phase. These two things you need, because magnitude tells about the amplitude of that particular phasor, and theta tells about its location in space with respect to time. Means where that particular phasor is located at that particular moment, that particular time. So that is obtained by theta. So now this can be also represented as the given complex number can also be represented as like this. You have A is equal to the magnitude A and angle theta, or R angle theta. So this is what we call as the polar representation of this particular complex number. This is the polar representation, right? So if you see in this particular equation, in this particular diagram, this AB, okay, so let us see this further. In, triangle OAB, your AB is Y, which is equal to a sine theta, and your OB is equal to X, which is equal to a cos theta. Now these two can also be used here. So if you put this in the given equation, this one, so your R is basically equal to so these two have been obtained from this triangle here OAB. So AB is your this A, this one is perpendicular upon hypotenuse is sine theta, base upon hypotenuse is cosine theta, right? So this is what we have written here in this equation. Now, if you have a complex number which is a is equal to x plus jy, so this can also be represented as a is equal to your, now this is the magnitude basically. This is the magnitude. So this is equal to, we can write it like this also, right? So where we know that this mod of a is r, so we can write it as your r x, because x can be written as this one, okay, r cos theta plus j r sin theta. So a is equal to, r can be taken as common, so it is cos theta plus j sin theta. And we know that this particular part is nothing but it is exponential j theta, right? So a is equal to your r e raised to the power j theta. So this is also is known as the polar form, but this is we call as exponential form of the complex number. Right. So we have three forms of the complex number: rectangular form, a is equal to x plus jy. We have the polar form, a is equal to r angle theta, where r is this one. And then we have the exponential form, which is equal to, a is equal to your r exponential j theta. So if you see in all these, we need the magnitude and theta. So these two quantities are required. So it is very easy to find out the magnitude and the angle. So if you take some example here, so now we can solve this with an example. Now let us take some a is equal to 3 plus j4. Now the magnitude of this would be under root 3 square plus 4 square. So it is under root 25, which is equal to 5. And the angle theta is tan inverse imaginary by real, 4 by 3. So this is, if you calculate this with the help of table, this is 53.1 degree. Now, one more thing you have to remember while solving the complex numbers, you have to remember the quadrant also. So if you see the quadrant, this is the real axis, this is imaginary axis, this is your first quadrant, this is the second quadrant, this is the third quadrant, and this is the fourth quadrant. Now in this, if you see these 3 and 4 both are positive, so that means this phasor A is located somewhere. Let us say this is 3, this is 4, and this is, let us say, 3. So if you extend them and you have got an intersection point like this, so this intersection point will give you this intersection point will give you the phasor location. So here your phasor is located, right? So let us draw the phasor. So this is how you'll draw it. Okay, so the angle, this angle is your 53.1 degree. Similarly, we can take one more example to understand this concept. Let us take one more example. Let us take one complex number, which is this is, let us say, second part. A is equal to your let us take it as 5 minus j5, right? Now if you see this particular complex number, if you draw its quadrant or location, this is plus real, this is minus real, this is plus imaginary, this is minus imaginary. So this is, if you compare this with uh, x plus jy. So if you compare this with x plus jy, so x is equal to 5 and y is equal to minus 5. right? So if y is equal to -5, so that means y is somewhere uh, here. This is -5, for example, and x, this is 5, for example. Now, if you draw it, and this intersection point will give you the phase, and this is your angle theta. Now, that means this phasor is located in fourth quadrant. A is located in fourth quadrant, right? Now, uh, so let us find out the magnitude. Magnitude can be obtained in the similar manner, and this is your 5 square plus 5 square means the real square and the imaginary square. So this would be equal to sorry, not 2, uh, it is 5 under root 2. This is the magnitude. And what about the angle? So theta is equal to tan inverse minus 5 by 5. So it is equal to minus tan inverse 1, right? So you can write it in two ways. Either you can write this one. This is your 2 pi minus theta, and this is your theta. So tan is 1 for 45 degrees, and this is minus 45. So theta is equal to minus 45 degree or 315 degrees. So any one of them is true. So the polar representation of this of given complex number is the polar representation is the magnitude, which is 5 under root 2, and angle is minus 45 degrees, or this can also be written as this, like this, 5 under root 2 angle 315 degrees. So both are true because your phasor is located in the fourth quadrant. So while solving the complex numbers in this way, you need to find out the location also, right? So let us take one more example here. Third example, a is equal to minus 2 plus j2, right? So in this, if you see, if you draw its quadrant location, so its quadrant location would be real plus imaginary minus real minus imaginary. So if you compare this with a is equal to x plus jy, so your x is equal to minus 2 and y is equal to 2. So that means x is somewhere at this point and y is positive. Now if you extend it like this, you'll get the phasor location. And this is your angle now, right? This is angle theta. So that means your A is located in second quadrant. So now you can find out the magnitude here. So magnitude is real square plus imaginary square. So this is your 2 under root 2. And the angle is tan inverse minus 1 by 1. Sorry, minus 2 by 2. So this is minus tan inverse 1. And now we can see minus tan inverse 1 is 45 degree. So this could be your what is this? This is more than 90 degrees. So theta would be negative for either minus 45 or equal to 135 degree, right? So this is theta. So your A in polar representation is your 2 under root 2 angle 135 degree. So this is how you can solve the complex number. This is how you can convert the rectangular form of a complex number to the polar form. And similarly, you can also, get the representation in exponential form by putting the value of r, means the magnitude, and theta into the relevant equation. So this is it for today's lecture. Thank you so much.